Hey class, welcome back. This is Mrs. Brunk. We're going to continue working with our linear systems today, and we're going to begin with modeling with linear systems. So we have actually been doing a lot of modeling with linear systems, and we've been taking some real life scenarios and writing systems that can be used to solve and answer these real life questions. So we're going to continue work with that, and our essential question is how can you use systems of linear equations or inequalities to model and solve contextual problems, in other words, real life problems. Real world situations can often be modeled by systems of equations. Usually information about prices and the total number of items purchased is given, and the system is solved to find the number of each item purchased. So we've worked on that in a couple different assignments, and we're going to continue kind of looking at more problems like that. Again, the more you see of these, the better you get. And then we're going to kind of work in some inequalities into this lesson as well. So Joe goes to the store to buy jeans and some t-shirts. So there's two things he's wanting to buy: jeans and t-shirts. The jeans cost $40 each, so jeans are $40 each and t-shirts are $20 each. If Joe spends $160 on 5 items, how many pairs of jeans and how many t-shirts did he buy? So when we think about writing a system, we have 2 unknowns. Looks like we want to know how many jeans and how many t-shirts. So our 2 unknowns would be jeans, let's say we call it J, and t-shirts we call T. And so if we have 2 unknowns, we need to have 2 equations that describe those 2 variables. And notice that one of the ones they tell us about is the number of total items. So it says that Joe purchased a total of 5 items and spends $160. So he spent a certain amount on jeans and he spent a certain amount on t-shirts, and that's the total amount spent. And so we think about the amount spent on the jeans. He spent $40 for each pair of jeans, and he spent $20 on each t-shirt. And the total amount spent was $160. So these are dollar amounts here: 20, 40, and 160. A lot of times when we write equations, we'll leave those off. But just to keep in mind, those are all relating anything that has to do with the cost of those items. So we put those all into one. That's like our cost equation. Now the other equation is, so we have that, the 40J plus 20T equals 160. And then we also have just the number of items purchased. So we bought a combination of jeans and t-shirts that add up to 5. So there's 5 total items. So this is a system that's perfectly set up to solve with elimination. So for instance, we could take that bottom equation, we could multiply the whole thing by, say, -20 or -40. So if we did -40, okay, then our new system would be, well, we have the original one, or the first equation, 40J plus 20T equals 160, and multiplying that bottom by -40 would give us -40J minus 40T equals -200. And then all we have to do is add our equations to solve. So we see that the J's are going to cancel. The T's, I have -20T, and then 160 plus -200 is going to be -40. Dividing by -20, I get T equals 2. And that means there's 2 t-shirts that were purchased. And since there's a total of 5 items total, right? So the number of jeans must be 3. So we have J, or jeans, 3, and T's, 2. So that's the type that we have looked at in the last couple assignments. Been equations that kind of lend themselves to the standard form equations. And then in the first applications we looked at were ones that were more slope y-intercept form, where there was maybe like a starting amount, like say a delivery fee, and then a per item charge or something like that, or per hour charge, like there's a membership fee and then a per month charge. And those were all equations that were in like a slope intercept form, and then we use substitutions to solve them. So in both are very common situations that come up. So modeling real-world constraints with systems of linear equations. So you can model real-world constraints such as the number of items needed and the amount of money one has to spend with systems of linear equations. So here's our first example. Write a system of equations to represent the situation and then solve the system. Bobby will buy coffee and hot chocolate for his coworkers. Each cup of coffee costs $2.25 and each cup of hot chocolate costs $1.50. If he pays a total of $15.75 for 8 cups, how many did each did he buy? So again, this is when we look at to write our system, we have one that has to do with the total number of items that were purchased. And there's one that's the cost, right? So our number of items, number of cups that were purchased, well, if we call them coffee and hot chocolate, or C and H, C plus H is going to equal a total of 8. Whereas the cost, which is our other piece of information that we have, is each cup of coffee is $2.25, plus each cup of hot chocolate is $1.50, and a total of $15.75 was spent. So there would give us another system, which at this point we're not going to take the time to solve that, but just actually setting it up. Once we get it there, then the solving we've spent a lot of time on, and we're probably getting really good at that. This would be definitely another one where we'd want to use elimination. But again, it's just kind of identifying like what are your two, like what are your equations going to be? What are your two facts that you know? And in this case, the facts were the number of items purchased and then the cost. So two different equations, one for items, number of items, and one for the cost, that together then create a system of two equations and two variables that can be solved. Let's look at one more, and then we'll have a you try question. So a student is buying pens and markers for school. Packs of pens cost $2.75 each, and packs of markers cost $3.25. If she bought a total of 6 packs and spent $17.50, how many of each did she buy? So there again, we've got a one equation is going to describe the total number of packages. So P represents pens, M represents markers, and there's a total of 6 packages purchased, right? Then the cost, well, each package of pens costs $2.75. So $2.75 per package of pens, and $3.25 or plus $3.25 times M, which is the number of markers, and then a total was spent of $17.50. So there again, we have another system of equations that we could solve using elimination. So here's a chance for you to try your hand at it and write a system and give it a try and solve it. So once you write it, solve to find out how many of each of the two types of machines, computers and printers, did the company purchase. So pause the video now and give number 4 a try. So here's our system. C plus P equals 16. That's the total number of items. And then the cost equation that's associated with that, 550C plus 390P equals 8160. I solved by elimination. I eliminated C first by multiplying the top equation by negative 550, but there's other ways you could do this as well. You could use substitution. You could have solved your top equation either for C or for P, or maybe you could have eliminated P first. But at the end of the problem, you still should come up with the same answer, and that was that the purchase involved 4 printers and 12 computers. Now, some of these real life problems kind of lend themselves more to systems of linear inequalities, linear inequalities. I should have emphasized the inequalities part of that. When we think about the lesson that we learned in just in the prior class, I kind of mentioned that, when you think about some of these scenarios, maybe you say you want to purchase these things and you have at most this amount to spend. Now, it doesn't mean you have to spend it all. You could spend less than that, but if you have, say, a budgeted amount, you just don't want to go over that. And that kind of lends itself towards inequalities, because you could maybe spend less than or equal to this given amount or whatever. So there's a lot of real life situations where inequalities really better represent the situation. So these next examples will look at that. So you can use a system of linear inequalities and its graph to model any real world situations. So Sue is buying t-shirts and shorts. T-shirts cost $14 and shorts cost $21. So let's say we're going to call the t-shirts T and the shorts S. T-shirts cost $14 and shorts cost $21. She plans on spending no more than $147 and buy at least 5 items. So she wants to have at least 5 items to introduce to her wardrobe, but she doesn't want to spend more than $147. So show and describe all combinations of the number of t-shirts and shorts that she could buy. So first write a system and instead of saying X, we're going to say what would have been X would be t-shirts. So we'll say T be the number of t-shirts, and we'll put T down here on the horizontal axis. When you are graphing these, and it's a linear combination, there's not necessarily one variable over the other that would be like the x-axis variable. So I usually just whichever one's listed first. Now, of course, if there was a slope y intercept type of real life situation, then of course, you'd have one that was kind of the clear independent variable or the clear x coordinate. But here, when it's just linear combinations, either one could be, and the only difference would be just the graph would be sort of inverted. But we'll call the T be the x-axis or the horizontal axis, and then the shorts we'll call S instead, so we'll make that the vertical axis. So, and again, she wants to buy at least 5 items. So she's buying t-shirts and shorts, and she wants to spend at least, so that means she wants this combination of t-shirts and shorts to be greater than or equal to 5 items. Okay, so 5 items would be okay, and anything more than that would be okay. But at the same time, she doesn't want to go over this budget, and the budget is $147, right? So she wants the combination of $14 t-shirts and $21 shorts to not exceed her budget, so to be less than or equal to $147. So when we have inequalities, as we saw in the prior lesson, the only real way to solve that, because there are infinitely many possibilities, is and in this case there might not be infinitely many possibilities because you can't have like fractional shirts that you buy. But you actually will graph and look for the solution set, or in other words, the overlap of the two inequalities, and those would be your possible solutions. So first of all, the T plus S is greater than or equal to 5. Well, the easiest way to graph something like that when they're in standard form is to just do the intercepts. So, and pretend, remember, we always want to pretend like these are equations because we're creating the boundary line. So T plus S is equal to 5 is what I actually want to graph for my boundary line. So if I put a 0 in for t-shirts, so that means I'm buying, no t-shirts. And if I was, again, pretending like this is an equality, then the number of shirts would be exactly 5. And if 0 shirts, then it would have to be 5, or 0 shorts, it would have to be 5 t-shirts. And so the boundary line is actually going to go through the x and y intercepts at 0, 5, which is right here, and then 5, 0. So we've got this line here that's going to connect, sorry. It's going to connect these points. And notice I didn't extend this line out, and that's because really only positive integer values here would make sense, or I guess, or 0. You could buy, I guess, 0 of these things. So we wouldn't want this to cross outside of the, the first quadrant there, because everything's positive in this situation, right? So that makes sense. And if I were to just be looking at that alone, I want to be above 5 or at 5, then my shading would have been above this line, right? But I also have to take into account this budget that I have. So the budget is the 14t plus 21s has to be less than or equal to 147. So to graph this, again, remember I'm going to pretend like this is an equality to get the boundary line. And both of these lines will be solid because they're or equal to graphs. But for this one, I want to see what my intercepts are. So see if those turn out nice. I suspect they are. So if I bought 0 t-shirts at $14, then the number of shorts I could get would be 147 divided by 21, which would be 7, right? And if I put in 0 for shorts, I didn't buy any shorts, in other words, okay, then how many t-shirts could I buy with that budget? Well, 147 divided by 14 would actually be 10.5 t-shirts. Now, you can't really buy half a t-shirt, so that one doesn't really, that specific point doesn't really make sense. But for graphing purposes, we're going to go ahead and plot the intercepts. One at 0, 7, which would be here, and then the other one would be at 10.5 and 1, so that would be right about here. And then connecting that, okay, look like this. And because I can't go over my budget, I would want to be shading below this line, right? And so essentially what my possibilities are right in here in this region between these two lines. Okay. So the only ones that really make sense, though, within this region are the ones where those grid lines cross, right? Because then those are full integer numbers of t-shirts and shorts. So like, for instance, this one is a possibility. That would be 4 t-shirts and 2 pair of shorts. Or this one right here, which would be 3 t-shirts and 4 pairs of shorts. Or maybe say this one right here, which would be 8 t-shirts and no shorts, or 7 t-shirts and 1 pair of shorts. But any of these, what are called lattice points, are all possible values here, because as long as they're integer values, these are all solutions. Now, even values that lie on the lines, if they're integer values, will work as well. So, for instance, maybe this one looks like this is right on some nice integers, and if that actually does work in the inequalities, that would be a possibility as well because of the solid line. So what I'm really doing here is I'm actually just finding possible combinations that she could buy and meet both criteria at the same time. So any of these listed. So again, I could go with, say, how about 5 and 2? I could get 5 t-shirts and 2 shorts. And in that, I'd meet the criteria here of being at least 5 items. In fact, there's 7 items. And the same thing here, I'd stay under my budget because buying 5 things at $14 and 2 things at $21 would lie under $147. So when we do solve things like this where we're not required to meet an exact value of number of items or costs or whatever, then we are creating a region with many possible solutions. And let's try one last example. So John has to buy 2 different kinds of rope. Rope A costs 60 cents per foot and rope B costs 90 cents per foot. So basically our unknown are the rope A and rope B. We'll use those variables. John needs to buy at least 15 feet of rope. but he wants to spend no more than $18. Show and describe all combinations of the number of feet of which type of rope John can buy. First, write the system. Let X represent the amount of rope A and Y rope B. And instead, again, I really like to use A and B if it's called rope A and B. I'll just know that because they designated X to be rope A, I will make sure that rope A is on the horizontal axis and rope B is on the vertical axis. I just think it's really easier to stick with those variables. So I have a criteria about the amount of rope, and I must have at least, so in other words, greater than or equal to 15 feet of rope in total. And that can be a combination of amounts of A and B, but that have to together be more than 15 or 15. So our A plus B must be greater than or equal to 15. Now, as far as the cost goes, we want to stay under our budget of no more than, so less than or equal to $18. And we know that for rope A, we're going to pay 60 cents a yard. Oh, is that a yard? Or foot, excuse me. 60 cents for A, plus 90 cents for, let's change this to B, when that must be less than or equal to 18. So again, if these were equations, if we wanted exactly 15 feet of rope and we wanted to spend exactly $18, which again is not probably the most realistic situation. So this is much more realistic than these systems of equations for the most part. So what this is going to do is give us possibilities, choices that we can make that still meet both criteria. So again, the first inequality I'm going to graph will be the easiest one, and that's the one A plus B is greater than or equal to 15. So we pretend like this is an equation, A plus B equals 15, and we're going to graph that, just finding the intercepts. So say we bought 0 feet of A, we have to buy 15 feet of B to be exactly 15. And if I bought 0B, I'd have to get 15A. So those are the real easy intercepts to find. They're going to be at 15 and 15 on both axes. So there's, right there, that's the 0, 15. And then the 15, 0 would be, let's see, these are scaled by 2s, so right there. And the line that connects them would be a solid line. Because we could get exactly 15, but we could also get more than 15. And so the shading here is going to have to be, we want at least, so we want it to be, the combination to be greater than or equal to 15. So that would be shading out here, more than, but above the line, right? Now the other one, we want to stay under that. And so again, finding this one, we probably are best off again finding the intercepts. So assuming, let's say you purchase no A, how many could you buy of B? So if you purchase 0A, so this whole thing turned into 0 right there, right? Then how much would we have of B? So what that would look like would be 0 plus 0.9B. And again, we remember that we think of this as if it were an equality to do your boundary line. So it would be 0.9B is equal to 18, and that means I'd have to divide both sides by 0.9. And that would be 20, because 0.9 times 20 is exactly equal to 18. And then instead, if we bought 0B, then our equation would look like this, and in order to find out how much of A we would have to purchase to spend the exact $18, we'd have to take 18 and divide by 0.6, which would then mean we'd have to buy 30 of A. So graphing those intercepts would be at 0, 20, that's way up here, and then 30, 0, which is down here. And then because this is a budget line and we can't go over our budget, we know that we want to stay less than or equal to 18. So we're going to shade below it, And that means all of this in here is called the feasible region. That just means what's possible. So anything in here, even along these axes, so right here, here, anything in between these lines are all possibilities. So there's really no way to list all those possibilities. I mean, there is. It would take a long time to list all the possibilities. So the possible solutions are everything that's in this shaded region that's like an integer combination. And I guess, technically you wouldn't have to buy full feet. So really, actually anything within the shaded region would work, because you could say, for instance, purchase 4.5 feet, because I assume they're on like big spools and they just pull them out and they measure. So usually things that are measurable like this, you can actually include one, like decimal amounts. So you wouldn't have to have all nice full integer values. But if you wanted to list some possible, not the possible, but some possible, if you wanted to kind of designate, just some that are integer values for A and B, like here's a possibility right there, that would be 2 and 16. So 2 and 16 would work. That means 2 of A and 16 of B. You could say pick one right here. This one would work. That's 18 and 2. So 18 of A and 2 of B. Okay. And really anything that's either on either of those lines, because they're both solid, or anything that's in the shaded region will work. So that just opens up lots more possibilities, because we're not saying you have to spend every single cent and you have to buy this exact amount of items. And it's just, again, it's much more reflective of how real life problems work. So that actually does it for today, and I'll see you in class.